Hello, my name is John Cleland. I'm a retired electrical engineer. I worked for TVA, Tennessee Valley Authority, for 37 and a half years, and I worked the entire time in the transmission planning department of TVA. I worked in pretty much every capacity in that department. I think the only thing I didn't actually perform were dynamic stability studies. About 12 to 14 years ago, we were still using an old Fortran program to calculate transmission line impedances. And in fact, that program, which was originally a Fortran program for mainframe, I had converted it several years previously to a PC-based Fortran. But it was old, it was clunky, very hard to enter the input data. You had to edit the file manually. And so I began looking at whether or not to replace that with a newer program. And initially I tried deconstructing or reverse engineering the existing source code for that program, but that was very difficult to do. So the next thing I tried was starting from scratch, trying to perform my own mathematics. And it quickly became obvious to me that was going to take some time that I really couldn't afford to do at work. So I took it home, and on my own time at home, I taught myself how to perform the mathematics to do transmission line impedances. Once I figured that out, I carried it back to work, and using the only platform I had available, software platform, I created a Visual Fox Pro program to perform transmission line impedances. Now, TVA used that program for several years, probably 10 years or more. They hired a programmer a couple, 3 years ago because Fox Pro is a dying software base. They hired a programmer who reprogrammed it entirely. I had nothing to do with that. I wasn't involved in it at all. I have seen it run. It's significantly different. It has a few bells and whistles that they wanted to add. I think it's done in C#, maybe with Silverlight as the visual basis for it. But after I retired, I decided, just because I'm partly interested in it, I decided I'd try to write my own program. So using Visual Basic, I began experimenting with writing my own program. And the program that I wrote mimics the original Fox Pro program that I wrote. Of course, I had to start from scratch, but at any rate, it looks a lot like the old program. I've made a few changes, a few enhancements, a few things done differently. But at any rate, I want to show you my program and see if I can generate some interest. Now, the thing about my program that I'm most proud of is that it's an extremely efficient program. Problem setup goes very fast. You know, when you're doing transmission line impedances, finding all the information, the location of the transmission lines relative to one another, the height of the towers, the arrangement of structures, all this stuff takes some time to get together, and you don't want to spend a lot of time putting the problem together. And that's what my program does, I think, better than any other program I've seen, commercial program that I've seen. So I'd like to show you my program and see if you'd be interested in it. So I'm going to begin the demonstration with the program already running. Now I'm going to open a file, a sample problem, so that you can have a basis for seeing what I'm talking about better. So the upper part of the screen is the management area for the user interface. The bottom part of the screen is the corridor pane. You can see that there are 20 little buttons here. That's 20 sections. Circuits, there are 15 buttons for circuits. That says that the program can work up to 20 sections with 15 circuits per section. You can see here a legend. Green is selected, red is in use, white is unused. So that looking at the buttons, or the dots here, you can see that there are 5 sections in this problem, and section 1, which is the selected section, has 5 circuits in section 1, and circuit 1 is the selected circuit. You can see that circuit 1 is dashed and circuit 1's name down at the bottom is in bold. So you know which circuit is actually selected. At the top you can see row values. This is row value for section 1, row value for section 2, row value for section 3, etc. I've got this particular run set up to use a system frequency of 60 Hertz and a base MVA of 100. When you get per unit or percent values in the output, they will be based on a base MVA of 100. The corridor width is presently set at plus or minus 500 feet. You can see plus or minus 500 feet. I can make it wider, and you see the tower pictures get closer together. I can make it up to 2,000 feet to the left and 2,000 feet to the right. Or I can go down such that I go as low as plus or minus, and if you try to go too far, you get a message, plus or minus 125 feet. And now you know that there are things that are off the screen. You can't see all of it. I make a little red arrow pop up that says there's something off the screen on the right-hand side, and the arrow is actually a button. You can punch the button and it will reduce the width of the corridor one step each time you punch the button. Height, likewise, I can raise the roof, so to speak, up to 400 feet, or I can lower it down as low as 50 feet. Again, if something is off the screen, off the corridor pane, you can punch the little red button and it will, just like pressing this button, it will give you changes in the height of the corridor pane. Now let me move just for a moment to the wires and towers. These values are in little files that are separate from the program. I'll show you those later and show you some things you can do with it, but you can add, delete, there's a menu item to alphabetize, but these are conductor values, resistance, reactance, and wire diameter that are used in calculating impedances. Towers, there's a edit towers form, and this tower you see example variable sag. Almost all transmission lines, three-phase transmission lines, the three phases all sag the same. But if they don't, you can turn auto sag off and you can enter the sag independently such that you can see each one of these phases has a different sag and the two ground wires have a different sag. But moving on to another, this is a 500 kV tower. There's the name, the phase A, B, and C positions, and the ground wire positions. Conductors per phase, spacing in inches, and the angle that determines how the bundling is spaced. And you can see a little note here that this is 3 conductors per phase. The sag values are determined by subtracting the vertical wire reference, which is 90 feet. That's roughly 90 feet right there, minus phase to ground clearance. So that's 90 feet minus 35 feet gives you a 55-foot sag. Moving on to some of the other tower definitions, there is a underbuild, 161 kV underbuild under the 500, and that's on the left-hand side. Here's the right-hand side. This is a single pole with 1 ground wire. Left-hand side of a double circuit, right-hand side of a double circuit, etc. So you can see that you can predefine all your towers, and then I'll show you in a minute how to use those towers in a problem. Okay, to begin the example, let me first switch over to a picture of the sample problem I'm working. You can see that this is a corridor that goes from Baltimore to Washington, beginning with the Baltimore 161 kV bus on the left, the Washington 161 kV bus on the right, and the 2 circuits that I'm trying to work are Baltimore Washington number 1 and Baltimore Washington number 2. Those are the circuits in bold. You can see that other circuits on this corridor is the Baltimore, New York 161 line, the Baltimore, New York 500 line, and the Baltimore, Pittsburgh 161 kV line. And I've divided the problem into 5 sections. Section 1 is out to the Annapolis tap. Section 2 is out to the point where Baltimore, Pittsburgh leaves the corridor. Section 3 is out to the point where the 2 New York lines leave the corridor. Section 4 is the final section where only the 2 Baltimore, Washington lines are on the corridor. And then Section 5 is the Annapolis tap itself. So if you're standing here at Baltimore looking down the line, this is what you'd see. Baltimore, Washington, or Baltimore, Annapolis tap, which is part of the Baltimore, Washington #1 line. And then double circuit on the same tower with it is Baltimore, New York, Baltimore, Pittsburgh, 100 feet away, Baltimore, Washington #2, 100 feet farther away, and then Baltimore, New York 500, 150 feet farther away. So if I click either the Circuit 1 button or the name itself, is also acts as a button. So if I click Baltimore, New York will be the selected section. You can see that the green dot changes to Section 1, Circuit 2, and you can see that the line we're working now is Baltimore, New York. So let me go back to Section 1, Circuit 1. You can see that this is the tower double circuit steel pole 161 kV left. Here are the phase A positions, A, B, and C phase positions, the ground wire position, the calculated sag based on vertical wire reference of 55 feet, phase to ground clearance of 25 feet. That calculates to 30 feet sag. And then there's a sag difference of 5. That says that the ground wires sag 5 feet less than the phase wires. So with the auto sag calculation turned on, all the sags, 25 feet for the ground wires and 30 feet for each of the phase wires, is calculated for you. The phase conductor is selected here, the ground conductor is selected here, and you can see that the phase wires and the ground wire #1 are the only ones in effect in this particular run. I can change the ground wire, for example, to 7 number 8, or I can change it back to 7 number 9. I can change the phase wire to whatever, and the phase wires and the ground wire lists are separate lists, just so you can get to what you want to do quicker. I can change to a different tower, and I can even pick a different circuit. Now, before I go much further, let me go back to the circuit names form. This is where all of the circuits involved in the problem are defined. There's the Baltimore Annapolis tap, the Annapolis tap to Washington, Annapolis tap to Annapolis, Baltimore Washington #2, Baltimore New York, Baltimore Pittsburgh, and Baltimore New York 500. This is a column that has check boxes for the lines that you'll summarize and print. So in this case, I'm only actually working the self-impedances for Baltimore Annapolis #1 and Baltimore Washington #1 and Baltimore Washington #2. So I should get 4 output pages for those 4 line sections, and each one of these will have mutuals with all the others, which will show up, but the self-impedances for these 3 lines will not be worked since I don't have them checked. I can add another, and I can uncheck these. Let's suppose I wanted to work Baltimore Pittsburgh. I could uncheck all of these, check that one, and then of course I would have to add the rest of the Baltimore Pittsburgh line, because that particular line isn't fully represented in this problem. One of the outputs is the phase domain output. The mathematics requires that you go through the phase domain calculation before you do the sequence domain. So I went ahead and actually output the phase domain results. You can turn on continuous transposition, but of course that only affects the phase domain answer, or the phase domain portion of the mathematics. So if I just click the Work TLC button, it tells me this file already exists. Files are TLI is the input file, sample1.tli. sample1.tlo is the output file. It already exists. You want to override it? I say yes. OHTLC work is complete. I can view or print the output. And you can see this is simply taking the text-based output file, reading it into a form. You can see here is a page break character, breaking the first page into the second page. But I also, let's go up to say 150%. Also give you a print preview and a print. And you can see that this is the output. There's the positive sequence, either percent or per unit. I'll show you later how you can pick between the two. And ohms. The zero sequence self-impedance, percent, ohms, miles. And of course, the Baltimore-Annapolis tap is only present in section 1. In section 1, that's section 1, circuit 1. Then we see the mutual impedances between it and the 4 other lines on that corridor. Now let me go down to the Baltimore Washington number 2 line just to show you how varied and extra information you get out of this. The total length of that line is 13.84 miles. But you get to see the impedance, the self-impedance of every section. Section 1, circuit 4, section 2, circuit 4, 3, circuit 2, etc. And you get to see the mileage for each section, the total miles, and the total impedance. Percent impedance for the positive sequence self-impedance, the percent impedance for the zero sequence self-impedance. And then when you get down to the zero sequence impedances, you can see that it's mutually coupled with the Baltimore-Annapolis tap only in section 1. The Baltimore Washington number 2 is mutually coupled to Baltimore-New York in sections 1, 2, and 3. Baltimore-Pittsburgh only in 1 and 2, etc. And you can see the mutual impedance for each section and then the total mutual impedance. And then finally there's some information down at the bottom that just gives you a little information about the worked line. Phase wires are 2 million, the ground wire 1 and 2 are 7 number 8 aluminum weld. Now let me close this and go to the input file, view print input. And I'm going to go ahead and put it in print preview mode. This is the input file. Again, like the output file, which is a simple text file, the input file is also a simple text file. Now it adds one feature. It is comma delimited. So here's your circuit information, and there's your check boxes. The first 4 checked, the next 3 not checked, and the voltages. The user initials. Then here is section 1, circuit 1. This is the full definition in the input file of section 1, circuit 1, section 1, circuit 2, section 1, circuit 3. If you have 2 files and you want to merge them together, and maybe you've done some rearranging of lines, you can actually take manually the 2 files and you can cut and paste and build your own input file. You got to be careful to watch section and circuit numbers, but it can be done. And then finally at the bottom of the file, let me get to the bottom at the bottom of the input file is a summary of each section / circuit definition, phase A, phase B, phase C, etc. It gives you how this is put together. So that's the input file. So let's go back to the program with the file open, and let's do just a little looking around. First of all, let's open the edit circuit screen. This is edit circuits for the double circuit left hand side Baltimore-Annapolis tap. Let's change the configuration of the circuit just a little bit. Let's say it's minus 16 feet for the middle circuit, and you can see that I've now moved phase B over by 3 feet. Of course, the other side will likewise, and let me use this as the selector button and change phase B to 16 foot. And there we have the same change over there. We can change the sag difference to say 15 feet, And when I do this, when I give it this value, you'll see the sag change on this circuit. Now I have to go over to the other circuit and do the same thing, change its sag difference to 15 feet. You'll see now that the two circuits have both their B phases moved over and the sag is different. Plus, if I want to change the vertical, let's say this is a real tall structure, 80 feet, and I go over to the other side and change that to 80 feet. I've got a very tall structure, and let's suppose it's high above some river or something, and so the sag ground clearance needs to be changed. So if I change that to say 40 feet, you can see both of those move up. If I go to the other one and change it to 40 feet. So these are changes you can make on the fly, not necessarily to the default towers or the original tower dimensions, but you can make changes to the tower dimensions after you've already selected a particular tower. Now let's look again at our drawing. Let's go to section 3, and you'll see that there's 1, 2, 3, 4 sections in section 3. Let's go to section 3, and you can see still there are 5 total sections in this problem. Section 3 has 4 sections, and I now have section 1 selected. Another thing I've done is I've totally flipped the order of the circuits. First of all, I've put the 500 line at center line 0 and put everything to the left of that. So the Annapolis tap to Washington is now circuit 4, and it's all the way at minus 250 feet on the corridor. The order in which you enter these is irrelevant because it keeps up solely with circuits based on their names. The names have to be identical in order for the circuits to be worked properly. So let's go back to section 1 and talk about something we can do. Now let's just suppose instead of being one circuit on one side and a different circuit on the other side, let's suppose that this circuit was actually 2 circuits tied together. Now how do you accomplish that in the program? Well, the first circuit is Baltimore-Annapolis tap. So if I go to the Baltimore-New York, which is the second side, the right-hand side, if I simply change that to Baltimore-Annapolis tap, that single change will cause those 2 lines to be worked together as parallel, electrically parallel. Now, let me show you one other thing. When I say, I haven't shown you yet how to add a circuit or a section. So let me do that. First of all, let me say that you don't have to do them in any particular order. I can add a circuit or a section 10 at this point. Of course, adding a circuit or adding a section is really a misnomer. All of these are available to you. The only thing that makes one an active section with a circuit is if there is a circuit in that section that contains a record with a circuit name. So let's just suppose, if you remember, the section 5 was a single circuit line, the Annapolis tap up to Annapolis. Let's suppose that's an old substation that's being moved a mile farther out. And I'm going to add an extra circuit to get there. Let's go to, say, section 10. Let's pick circuit 1. Let's make that Annapolis tap to Annapolis. Let's give it a, let's say this section is built with a horizontal steel pole 161 kV instead of the single pole construction that was in the first 5 miles. So I'll call that, let's say this time they put 1590 on it instead of the 954, and let's give it the 7 number 9 and 7 number 9 aluminum well for the 2 ground wires. Okay, now I'm going to deliberately make a mistake. Here is the circuit miles. I'm going to leave that 0. Let me put, let's see, circuit 5 was row of 800. Let's make 800. Let's make it the same. Okay, now I'm going to save this. It's a different file. Save as. I'm going to save this as sample2.tli. And it's going to tell me that the input data has changed and saved, but a new solution hasn't been attempted. Well, let's go ahead and do that. Well, there are errors that it'll give you during solution if there's a problem. Some of them are warnings. Some of them are fatal errors that will not allow the program to solve. And zero distance on a particular line section is not acceptable. So I'll have to go back. There's one fatal error and zero warning. So I'll have to go back and fix that. Data not work due to fatal errors. So I can go back and give that, say, 1 mile, say it's 1 mile farther over. And now I can work it. Let's view the output. Let's find, well, first of all, let's look at Baltimore-Annapolis tap. That's the one where we doubled up. Now, it's only going to say there's one section, one circuit in that line. But if you look down at the data, you'll see that it's actually using section 1, circuit 1, and section 1, circuit 2, both as part of that line. That's because we named section 1, circuit 1, and section 1, circuit 2 Baltimore-Annapolis tap. Now let's go down to the Annapolis tap to Annapolis. It's now 6.8 miles long instead of 5.8. There's 5.8. That's the first section that was already in there, and it's single circuit steel pole. And now we've got an additional 1 mile, and that's in section 10, section 5 and section 10. Section 6, 7, 8, and 9 are non-existent in the entire solution. And there's no need that they be filled out. You don't have to have a particular order. You don't have to have consecutive sections. The only thing that makes a section valid is a circuit name in that section. So that's how you add sections and add circuits. You just pick them and fill them in, and there they are. So now there are, if I go back to section 1, you can see that there's 1, 2, 3, 4, 5. There's 6 total sections in this problem. Just so happens that sections 6, 7, 8, and 9 are empty. If I go to 10, there is only one circuit in section 10. Now let's look at some of the files that go with this. Here is the phase wires file, and as you can see, the first 2 rows in the phase wire file are simply instructional information, and then begins the data. And of course this one looks eminently adjustable manually outside the program. All it is a conductor name, a resistance in ohms per mile, a reactance in ohms per mile, and a diameter in inches. So, you know, it's not really necessary that you edit this file inside the program, although you can. But this one's fairly easy to edit outside the file. But one of the real beauties of it, you can change the order of these conductors in any way you want to, such that when you enter the program and when this file is read at the start of the program, when you pick from a conductor list, it'll be in the order in which you pick, in which you set it up before you start the program, unless you, of course, if you alphabetize it within the program using one of the menu items. Now this is useful. It's also useful to do the same thing with towers. Here's the towers file. It has 2 descriptive lines at the start, and then the tower's name and all of its data. Now this has a pretty good bit of information, so you just about have to edit towers inside the program. However, you can edit the order outside the program. So once this table is built, once this file is written, you can go out, edit, even in Notepad. You can move this row up and that row down and this group of rows up, and you can set up your tower list in a convenient fashion so that the towers of like counter together, or towers of like voltages, whatever. You can do the order outside the program. The final file I want to show you is the defaults file. The defaults file is arranged a little differently. here is the variable name that is used inside the program, the value, and then a description. So if you want to set this up such that every time you enter, your user initials are the ones that are brought up when the program runs, you can do that. This is the system frequency. That can be changed inside the program, but it is also a default that's set up when this file is originally read. Wire frequency. This can't be changed inside the program. It's only a default outside the program. MVA base can be changed inside the program. And in the output file, you'll either have percent or per unit for the per unit type impedances as opposed to the ohmic impedances. So you can determine whether or not percent or per unit is the basis for those impedances. Mutual difference, you need to read the user's guide to see what mutual difference has to do with it. Quarter width, here's the initial quarter width. I showed you how to increase or decrease the quarter width, but you can set the starting width in the defaults file, the starting height. You can also set the starting location of the edit circuits window that pops up. Now once you move that window around inside the program, it stays at that point. You can close that form, open it back up, and it will still be in exactly the place you've put it. Then there's some, just to let you know, the text boxes and the numeric text boxes in this program are all user defined. I had to write extra software to define how those operate, and you can decide whether or not the initial value of the text mode is true or false, and there's the description of it. The num mode is true or false, and whether circuit names are capitalized automatically, or whether or not tower names are capitalized automatically inside the program, or whether wire names are capitalized automatically inside the program. Then finally there's a disclaimer code word. When you first get the program, you have to answer a question that you've read the disclaimer, and then it'll rewrite this file and change that code word there. So that's my program in a nutshell. I hope you found it interesting, and I'd be more than happy to send you a demonstration copy. Let me move down here and show you. Here are my email addresses. I've got a Gmail address and another address. I live in Chattanooga, Tennessee. The local power board has a fiber optic system that I'm on, and I've got an email address with them. I can send you a demo program. The demo expires in about 3 months or whatever I set it to based on your computer date. And the demo outputs only 2 sections by 2 circuits. Now, I have 3 versions of this program. I can compile it 3 different times and get 3 different versions of the program. One is a 2x2 output. That's the least expensive version. Then there's a 5x4, 5 sections by 4 circuits output. That is more expensive. And then the ultimate is, of course, the 20 sections by 15 circuits. Well, I hope you enjoyed my video, and I hope you found that the overhead transmission lines constant program is interesting and possibly something you could use. Just before I end this little video, I want to mention one other thing. There is another program that I'm working on, and it is only partially completed and will remain only partially completed because it is a gigantic undertaking. And actually, I'm looking for someone possibly to partner with, or someone to sponsor me. At any rate, what it is a transmission system model database. That again is something that I've got a tremendous amount of experience with at TVA. I wrote the program that they presently use for their transmission system model in transmission planning, and I'm going to try to put another YouTube video up of a demonstration of what I've done so far on that program. So take a look at that, if you will, after you look at my overhead transmission line constants. Appreciate the interest. Thanks a lot.